Okay, so welcome to semantic session. So the first speaker is Jai Lu from Zhejiang University, and she will talk about formal semantics of eBPF instruction set architecture.
So hi everyone. Hi everyone, I'm glad to be here and share our work on formalizing a complete semantics of eBPF instruction set architecture for Solana. First, I would like to introduce the background. Solana is a third-generation high-performance blockchain platform. It provides a fast execution environment based on an eBPF-powered virtual machine written in Rust. However, as highlighted by security audits, the Solana eBPF VM is still not formally verified, leading to risks such as infinite loops and branch handling bugs. This motivates our work to formalize the semantics of the Solana ISA, and thus we can prove the correctness of its virtual machine. And this is the workflow of the Solana eBPF VM. Smart contracts are first compiled into bytecode and then checked by the verifier, and finally will be executed either by the interpreter or by the x64 just-in-time compiler. So our work at OOPSLA 2025 focusing on providing the eBPF semantics, while our earlier work at SPLASH' 2024 provides the necessary x64 semantics for the just-in-time compiler. Our goal is simple yet fundamental: to build a rigorous machine-checked foundation for understanding, verifying, and securing the Solana eBPF VM. And for the related work, let's first look at Linux eBPF. eBPF stands for Standard Berkeley Packet Filter. It basically lets you run sandboxed programs inside the Linux kernel, so you can add new features or monitor things without actually changing the kernel itself. When it comes to Linux eBPF, there is already a lot of research out there focusing on the verifier, interpreter, and the just-in-time compilers. But for Solana, this research is still quite limited. Most existing work depends on testing or fuzzing, and so far there hasn't been any formal verification for the Solana eBPF. Now let me talk about the challenges we faced. First, at the instruction level, Solana eBPF is a bit different from the Linux eBPF. It adds 13 new instructions, and some of the existing semantics are also changed. Second, at the Rust implementation level, things get tricky because Rust semantics are quite complex, and sometimes they don't fully match the definitions in Isabelle. For example, operation flag integer division and modulo behave slightly different. Finally, at the verification level, we don't yet have a trusted compiler to make sure that our formal model faithfully reflects the original Rust implementation. Now, to address these challenges, we've made the following contribution. First, we provide a complete formal semantics of the Solana eBPF instruction set architecture. All 116 Solana OP codes formalized and their semantics mechanized in Isabelle Hall. And second, we built a semantic validation framework to check the consistency between the Isabelle semantics, Isabelle formalized semantics, and the Rust implementation. Third, we demonstrate some applications of our formalization. And based on the semantics we developed, we further model and verify several Solana components. For example, we check the consistency between the assembler and the disassembler, and so on. Now I'll move on to the formalization of the Solana eBPF, or SBPF for short. First, for the syntax, we defined several basic components: registers, memory block, and instruction forms. It's worth noting that the common ISH is shared between all versions, while some instructions are version-specific, like the signed and unsigned multiple high and low double word are specific to version 2. And we also describe the program state. Each state contains 5 parts: the register state, the memory model, the stack, the version, and the call map. And now we move on to the semantics. Our approach is directly based on the source code. For example, here's the negate 32 instruction in Rust code, and we turn this behavior into a semantic rule. which describes when the instruction can be executed and how it changed the program state. Finally, we mechanize these rules in Isabelle Hall so that our semantics can be checked by the proof assistant. And we use small step operational semantics here. For example, here are some arithmetic logic unit instructions. And I won't go into details here, and you can find more in the paper or we can discuss later. Now we come to the third part, validation. The key question here is how do we make sure that our formal semantics is consistent with the original Rust implementation? For example, in some cases, a single instruction can actually be interpreted in more than one way. We need to find out the exact correct version. And in other cases, even if you get the correct translation, you will find that some simple operators like modulo behave differently in Rust compared to Isabelle definitions. So that's why validation is crucial. It helps us bridge the gap between the two systems, the semantic gap. And to solve this problem, we made the semantics executable by generating OCaml code directly through the Isabelle's built-in code extraction facility. We first conduct the program-level validation by running the Solana official test suite. It includes 114 normal cases and 32 exception cases. We have to exclude 14 cases because they require modeling Solana's built-in system calls. And furthermore, we also perform the instruction level validation, which means that we execute one instruction at a time, both on OCaml and Rust, and compare the resulting register state and memory model. We tested all the instructions except call and exit, since they require a full Solana program structure. And in theory, this framework can support any number of tests. And each round can run over 100,000 cases. And we've completed several rounds so far. And all the results matched perfectly, which shows that our semantics is valid. When we are using the extracted code, we actually found it quite hard to work with. For example, simple natural numbers ended up in deeply nested constructors that are difficult for humans to comprehend. This makes the extracted code difficult to integrate with our systems. So we introduced glue code. Basically, it's an interface layer that connects Isabelle with standard OCaml code. It wraps the Isabelle's complex types and converts them into integers. We use the wrapped Isabelle model to extract OCaml code. Until now, it's still hard for direct use. So we add another glue code by translating OCaml ints into Isabelle ints, and so that we can feed the test cases in normal way. Therefore, the extracted OCaml code can be much easier for you to use for our validation. And in the fourth part, we show how formal semantics can be applied. First, we apply to the assembler and disassembler to prove the correctness of the translation between the assemblies and the binaries. Second, we applied it to the verifier to make sure that the interpreter executes without errors in one step. And third, we use it for the x86-64 just-in-time compiler, where we validate the compiler correctness for Solana's basic arithmetic instruction to x64 binaries. And for evaluation, the overall effort is 11 person-months in total. Most of the effort, around 60%, went into SBPF verification. And about 30% went into the x64 binary formalization. And the remaining 10 was used for building the verification framework. We also report issues back to the Solana community. First, we found that the interpreter and the just-in-time compiler lack proper version checks, which means instructions specific to version 2 could mistakenly run in all versions. And second, the assembler does not check the source register range, which break the consistency between the assembler and the disassembler. And to conclude, this is the first complete semantic study for Solana, fully mechanized in Isabelle Hall. We also built an extensible validation framework to ensure the semantics, the formalized semantics and the real-world implementation are consistent. Finally, our work opens the door for broader applications, including formalization of several Solana components and the verification of properties. And thank you so much. This is the QR code for our GitHub repository. Anyway.
So we have time for a couple of questions. Any questions? Yeah, you can use the microphone.
Thank you for the talk. It's kind of a minor question. Why are there differences in the module function between Russ and Isabel? Like, it feels like a very simple.
It's hard to. You can see this form. We have listed the different results in the modulo operator behavior. As you can see, the same equation, this in Rust will end up in -1, but in Isabel it will be 9. So this is a kind of sometimes the modulo end up with the positive number, and sometimes it always ends up with a -1.
Okay.
Yeah.
Thank you.
My question is, so you have this kind of way to essentially verify, give the semantics to a Rust program in a sense. Did you struggle with some of the Rust specific features, so like say borrowing or mutable references and so on?
Actually, because it's Rust to Isabel, so Isabel doesn't have the ownership system or borrow checkers, so we don't struggling with the ownership system actually. If it was the other way around, then we would have to consider this problem.
Mm-hmm. Okay, thank you.
Thank you.
More questions? Okay, so let's thank the speaker. We'll begin in 2 minutes at 4 o'clock.
Did you have to turn it up? Thank you.
Okay, so our second speaker is Alex Cavos from University of Bristol, and he will talk about algebraic effects.
Thank you very much. First of all, apologies. This is a talk about denotational semantics, okay? So it's about three things. It's about adequacy, that's clearly a technical thing. It's about algebraic effects, which you might have heard about. And it's revisited, which means someone else has done it before me, but I've done it again, and I'll explain how. So, oh no. Oh, no. Slideshow, there we go. Okay, so what is adequacy? When you do semantics of programming languages, you usually do a little operational semantics. And often, when you do operational semantics, you've got some terms, and they step from one to the other. What's great about that? It's easy, it's nice, it's perfectly understandable. What's bad about this, it's almost impossible to reason about, as anyone who's done any program verification has ever thought about. Okay, but this induces a notion of operational equivalence. You know when two terms are the same, exactly when they either have the same reductions or in any context they do the same thing. Denotational semantics, on the other hand, is a translation to mathematics. You take your program, you map it to something in mathematics, and you have 2,500 years of tradition you can draw from. Okay? You only draw from the last maybe 50 years, but you still could. And adequacy is the property that if you discover something to be true using denotational semantics, then this will be true operationally as well. So for example, if you prove that the denotation of two terms is equal, then these terms should behave the same when you run them operationally. If you don't have adequacy, there's no reason to have denotational semantics. You need it to say anything at all about how programs run from the mathematical description. So this has been shown before for algebraic effects, but only finite true ones, by Plotkin and Power in a really influential paper, FOSSAX 2001. It was an invited talk. But the proof was difficult, and it only covered certain things that I wanted to do more of. So I wanted to do functional logic programming. There'll be a paper later this year, and that has an infinitary algebraic effect, which you couldn't do without proof. So I set out to do a simple logical relations proof, as simple as it could be, in order to cover this case. But I also did a lot more in the process. Okay, so really quick recap. What are algebraic effects? You might have heard a lot of things about them. The idea of function programming is that you've got a closed program, you put it in GHCI or your favorite functional language, out pops a value. Algebraic effects do much more than that. Algebraic effects are really just system calls. An algebraic effect is something that you issue, there's some kernel, hypervisor, whatever you want to call it, which takes this signal, does something, gives you back a value, and then you continue with this value. So I will use that notation, op, for an algebraic operation, which sends sigma and receives tau. These sigma and tau have to be serializable, they have to be first order things. It's really important that they are. If they're not, you get into trouble. For example, to have a global memory that holds one natural number, you can write this natural number and receive the unit value, or you can read this natural number by which you send the unit value and you get back a number. So here's a little program in this notation. Write to read x, return the successor of x. Algebraic effects produce these things called interaction trees. You can see an interaction tree on the right. The first node is the write instruction. Then you do, that only has one possible continuation. Then you read, and depending on what you read, you return the successor of that. If you read 0, you return 1. If you read 1, you return 2, and so on and so forth. There's nothing in algebraic effects that tells you your memory has to be correct. Okay? So your memory could return the wrong value. That's an equation that you put on algebraic effects later on. Okay, one of the main technical innovations in this paper is using something called call by push value. I don't have time to go into it here, but if you don't know about call by push value and you like effects, learn about call by push value. Just go away and learn about it today. It's an amazing innovation. It fixes almost every technical problem you might have. It fixes the order of things. It's wonderful. But the main thing is you've got values on one side, which are immutable mathematical things like numbers, sums, products, and also these magic things called funcs, which are really just a frozen computation. And on the other hand, you've got computation types, which are really types that describe an imperative thing. The most basic thing is f of a, which a computation of this type will return a value of type a. Interestingly, a function here is something slightly effectful. It's something that pops an a from the stack and continues as something else. There was a fantastic talk earlier today by Max New on reading these as types of stacks. And you've got two kinds of terms, and if you know any Haskell, you'll recognize return and bind, but in slightly different notations. The operations are given by op, which takes an argument v of type sigma, which should be the right thing, and the continuation receives back something of type tau. This is the basic setup. And notice that operations can only have first order types, serializable things, no functions. Okay, you can give a really simple operational semantics. You can either look at this slide or I can just tell you. You have two reductions. One is your usual pure reduction of terms. The other one is the effectful reduction, which says I'm sending to my kernel the value v, and my kernel responds with my value w. And what you do when you have an operation, you can send that, receive w, and then you continue as the body with w substituted for x. That's it pretty much. Here's a reduction where the memory malfunctions. You send it, you write 2, then you read it, and you get back something else, so you return 4 in the end. You can use this to define a map that for each computation gives you an interaction tree, the thing you saw before. Okay, denotational semantics, I could talk about this for hours. I'm not going to talk about it for hours. It's a very simple, standard domain theoretic semantics. The details are unimportant. All you need is you need a monad which supports your effects. So you have a return and a bind, and for each op, you've got something that allows you to interpret this into tx. So this op thing would take the value, and then for each possible thing that you could return a continuation and give you something of type t of x, and you need to satisfy this equation. This equation is the fundamental equation of algebraic effects. If you read it, it says if you do an operation with continuation k, and then you bind into f, you could do the operation now, take the result and feed it into k, and then bind that. So effects happen now, and they are independent of continuations. If you don't have this, your effects are not algebraic. What's not algebraic? Continuations. Okay, control effects, not algebraic. If you have all this, for example, a state monad supports write and read. And if you have this, you can define continuous functions for values and computations. Okay, observational equivalence, or operational equivalence. Standard thing you would do in a functional language, you'd say two terms are the same. If for any context you can put them in, they give exactly the same values. Jim Morris did this in 1969, and we've suffered ever since. But this doesn't work when you have algebraic effects. So the solution to this is to say, well, suppose you have a way of lifting arbitrary relations between two sets to monadic values of the same thing. If you have that, then what can you do? You could say, well, m and n are equivalent if you plug them into any context, which you can think of as a testing bench, you compute the interaction tree, and then you evaluate it in your monad, that's related to the same thing for the other term, exactly when you've lifted the equality relation on values. So you generate related trees with the same values at the top, at the bottom. And this is not due to me, it's due to Francesco Gavazzo, who's done a lovely series of works on this. Okay, I'm just flashing this for your information. There's some axioms that this lifting needs to satisfy. This map from relations to relations. It's these axioms. They're not so interesting. For example, for the state monad, you say two memories are related. If for any input, they output, well, for anything that could be stored in memory, they output the same thing, and then the values they return are related. And these need to be compatible with everything in sight. It's unimportant what this is, you can easily derive it. Proof, biological relation. This is a very simple proof. This is the entire logical relation. There's nothing hiding here, nothing hidden under the sun. You define the logical relation at return types by lifting the relation of values, and you just need to decorate things just sufficiently. The usual lemmas go through, as you would expect in any standard logical relations proof. In particular, this is only a very little generalization of how Gordon Plotkin did it in 1977. And in particular, that proof is an instance of this for a very simple relator. Okay, this is also another slide not for you to read, but the idea, what I wanted to show you here, is that indeed the proof follows very simply. Nothing is hidden under the sun here. Well, everything is hidden in the particular axioms, but should the axioms hold for your relator, you can push everything through, pull these relations out. These relations, you know, compose to the value relation, and then you get that terms are related. rinse and repeat for the other direction, and you are done. Whole proof. Only took me a year. Okay, I will be finishing a bit early, I suppose, but what I want to do from now on, an important thing to do here is to lift this to recursive types. So the language we have, if you go back to the language, does not have recursive types. It does have recursion on computations, but not recursive types. Recursive types are really important, as referring to Max New's talk again. Max presented computation types as a sort of discipline of typing for stacks. If you have such a discipline of typing, you could have functions of variable arity, right? Something that JavaScript has now is fully typed and perfectly compatible with heriticians. So if you have recursive types, you can do all sorts of interesting things. But extending this to recursive types is always difficult. Logical relations on recursive types are difficult, at least if you don't want to make them guarded. But Andy Pitts' results from 1996, fantastic paper if you haven't read it, Relational Properties of Domains, should apply here with some contortions. The most important thing, though, is that a bunch of relational liftings used by many semantics researchers do not actually fit the relator framework. The axioms don't hold. So earlier today, for example, Pedro gave a talk where I think some of these axioms won't work. The question is, what's the difference here? There's a bunch of things like TT lifting due to Shinya Katsumata, or the code-density lifting more recently. They just don't satisfy these axioms. So you have to do something different. It's a bit of a question mark. If anyone knows the answer, I'd be happy to hear it. And finally, formalizing this might be a bit of a difficult thing, but it is certainly something on the cards. Someone would use suppose you'd have to use a domain theory library in Agda or Coq, which will be a little bit sad, but, you know, ways of writing more papers, I suppose. That's all I had. Thank you very much for your attention.
Okay, thank you for a great talk. Questions? Yeah, you can use my. Yeah.
Thank you. This is very interesting. So regarding the question of recursive types, do you envision some, I mean, since you have effects, you will need some step indexing, I guess, that goes beyond natural numbers. Do you envision that? Or?
I think it should be fine, but ideally I wouldn't like any step indexing at all.
I see.
So that's what the minimal invariant stuff does.
Okay. So
but
you
it's a bit difficult to do, and in particular it's not proof assistant friendly, which is why people have never done it. When people do these proofs and proof assistants, they use a guarded variant of domain theory, and they step index everything, and it all works out. But the cool thing is to do it without, and I don't know how.
Okay, interesting. Thank you.
Thank you.
Hi. Looks like a nice generalization. What I was wondering was, is it possible to relax the restriction that continuations have to be serializable values? Because sometimes you want to have operations that bind effectful things, right?
Yes.
If you want to encode things like control effects, you can do it with algebraic effects, but that requires you to do that. Is that a very hard generalization to do, or?
Okay, if I'm going to give you the mathematician's answer, which I often do, if your things are not countable, you don't have algebra. You don't have algebraic effects. You have something more than that. So you need at least some ordinal that bounds how big your values get. So the point is that these trees, these interaction trees, they're infinitely deep because they're co-inductive, and then infinitely wide because you have infinitely many results. If you don't put some bounds on the width, there's problems. Mm-hmm. It's an interesting problem. It's no longer algebraic effects. It's something else, I would say.
Okay.
Thank you. Question?
Thank you, Alex, for a wonderful talk. As far as I remember, adequacy can be formulated in equivalent ways, like when you don't have effects, like if you converge to a value, so if you're semantically equivalent to a value, then the operational semantic reduces to a value. So you can reformulate adequacy using predicates rather than relations, and then you can use logical predicates instead of logical relations to prove adequacy. So I wonder if this is possible.
After.
Okay.
Yeah, great talk. Thank you very much. I guess two things. One of them, I've seen some similar work modeling what are essentially the same as data flow circuits as monad streams. I just wanted to mention it. I think it's pretty different from your approach, but might be interesting. The other thing, I was wondering if you have any ideas about potential applications to, I guess, concurrent or parallel systems besides low-level circuits.
I guess this could be applied to that, but there's plethora of literature on data flow models for that, which I think correspond more to that. I'm really designed the thing with circuits in mind.
Sounds good. Thank you.
Okay, so let's thank the speaker. And the next talk is about dynamic wind for effect handlers and will be presented by David.
Okay, thank you very much. I'm very happy to be here and to present our work on dynamic wind for effect handlers. Of course, this is joint work by Jonathan Brachthäuser, Philipp Schuster, and myself. And as you can see by these fancy badges, we also have an artifact available. So I invite you to check out the artifact and have a look at the examples and test the implementation. Okay, before going in deeper, I want to give you some context. So the context switch might be easier for you. I'm in the fortunate position that we already had a great talk about effect handlers, but I'm still going to give you a short summary. We are in the context of lexical effect handlers. We have multi-shot continuations, and with these tools we can model complex control flow, for example, asynchronous programming, non-determinism, probabilistic programming, and many more things. So the idea we are presenting in this talk are implemented in the effect language. We also have a website, you can see it here. I also invite you to check it out after the session. And given this context, let's look at an example. We have the following program. We have a handler for the flip operation. I'm going to get how this is defined in a second. We have a mutable global reference that initially just has the value hello. And we have an if statement. And in this if statement, we are executing the flip effect operation. And then we are going to mutate the reference and in one branch append the word hello, the word world to it, and in the other branch we are going to append the word Singapore. And then in the end, in either cases, we are going to print out a result. So this is how you typically write the effect handler for the flip operation. You are resuming twice, so this might be perhaps a bit hard to get your head around. Once with true and once with false. So in the first resumption, we are executing the first branch, and in the second resumption, we are executing the second branch. Okay, so let's pause for a second and think about how we would expect this program to behave. Perhaps it's easier if we write another program for seeing how it should behave. If we are using stack local due to multiple variables, it should behave like here on the right side, because in effect, local mutable variables are backtracked by default. So in the first resumption, we are appending world to hello, and in the second resumption, the reference or the variable still contains only the string hello, but not world from the first resumption. So it's backtracked. So we are getting hello world and hello Singapore. But this is not what we are getting in the left example. What we are getting instead is hello world and hello world Singapore. So it's not backtracked. And this leads us to our problem definition. What we are trying to solve and what the problem is, we want to enable and allow backtracking or finalization of external resources. For example, as we have seen, global mutable state, or also maybe perhaps database connections or file handles. And we want to do so even in the presence of complex control flow, given by algebraic effects or effect handlers with multi-shot continuations. And the solution we propose is a bit similar, if you squint your eyes a bit, to try finally, from other languages, like Python, for example. But we have two cases, because with effects, we can also resume, so we have to think about both directions. And the solution that we propose is that we make the process of unwinding and rewinding the stack, so resuming and suspending a computation, observable. On suspend can observe when we are unwinding the stack, when we call an effect operation, and dually, on resume can observe it when we are rewinding the continuation back on the stack. And with this in mind, we can go back to the example and try to fix it. So now we are going to define the backtrack function. The backtrack function gets the global mutable reference and also the remainder of the program. In the body, we are going to use this new statement and the new clauses on suspend and on resume. And let's try to fill out the on suspend first. It's very simple if you just see it like this. We just get the current value of the reference and do nothing with it. But that's not true. We actually have access to the return value of the on suspend clause as a parameter in the on resume clause. So we are saving the current value of the reference when we are initially calling the flip operation. So when we call the flip operation, we have to traverse through this backtrack function. So the unsuspend is run and we save the value hello, and upon each resume we are restoring this value again in the on resume clause. And with this we get the desired behavior. We get hello world and hello Singapore. Okay, this is the semantics session, so let's talk semantics. How does this work? It is helpful, I think, not to show the step angulation, but instead be a bit more visual. So this is the stack. This is not a one-to-one representation of the program, but the important parts are here. We have the handler for flip. We have the suspend and on resume clauses. We have an empty handler. In this case, it's empty, but you can also have a handler here in the backtrack function, and perhaps also some other frames. Okay, so now imagine we are in the process of calling the flip operation. So that means we need to unwind the stack and find the corresponding handler. And because we are using lexical effects, we know exactly what handler we are looking for. So it's the label L1 or the prompt L1. So that means we have to unwind the stack until we reached the stack with number 2. Okay, so let's just pop the frames from the stack and push it onto the continuation. Okay, so now we have pushed all these frames, but now we have also pushed the on suspend and on resume frame. So now we need to pause what we are doing and execute the on suspend body. That means two things need to happen. We need, of course, to execute the program r.get, but also we need to remember somehow that we still need to continue with this unwinding process later on when this body is or has been executed. So we are pushing a new frame on the stack that is called unwind, fittingly, and this allows us to remember all the important information to later reconstruct what we were doing. And perhaps skipping some steps, eventually we'll just return hello after executing the on suspend body. And then we see that there is this unwind frame, which we want to return to, but this now serves as a reminder to continue this unwinding process we earlier started, but suspended briefly. And as I earlier said, we also need to save the value hello in the continuation so that we have access later in the on resume clause. So we are also saving it in the frame, and then we can resume with this original unwinding of the stack. And eventually we will find the correct handler, and then the handler will resume. So let's think about the other direction. How does it work? Interestingly, it just works the same, it's just symmetric. So imagine now we are resuming the computation. So we need to unwind the stack, rewind the continuation onto the stack, and then on this stack that then is computed, we need to return true. And again, now we have this finalization frame we need to put back on the stack. So we are using the same trick. We are pushing a new frame called rewind, and that also serves as a reminder to later continue this resumption process. And yeah, we are going to return just the unit value here, and then we see again the rewind frame, and notice we need to continue this resumption process. And then we can just continue doing so, pushing the frames back on the stack. And then eventually we will be back at the point where we started, and the program can resume. So much for this. We also have some standard theoretical results. We have progress, we have preservation, and also, of course, then also soundness. Perhaps a bit more exotic, we also have a theorem called resource safety. I think it's easiest to understand what it says by looking at an example. So what we did is we have some invariants that the user needs to uphold, namely that when having a resource, for example a file, the first thing the user should do is, in the suspend clause, is to close or finalize the file, and as last thing on resume, the user should reinitialize the file, in this case open it again. And if the user does this, then we have proven that all resources on the stack are actually initialized, so they are safe to be accessed, and all other resources are closed or finalized. So in summary, we have in our language, we have multi-shot continuations which require special care when adding dynamic finalization to the language. And for this, we have added 2 or 3 new clauses to the effect handlers, namely on suspend, on resume, and on return. And what I didn't show in this presentation, but what just arrives naturally, is that you can even call effect operations in on suspend and in on resume, and it still works. Okay, so now that you have seen the presentation, why would you even read the paper anymore? We still have some things to show. We have a type system for the language itself, for the calculus. We have a type system for the stack, for the continuation. And of course, we also have operational semantics. This might also be interesting for you to look at if you just are interested in how lexical effect handlers work operationally, even if you're not interested in the finalization itself, because this is very fine-grained and it might be informative to look at. And of course, we also have the proofs and the theorems. And here's the link to the paper. I invite you to look at it, and I'm happy to hear your questions. Thank you. Hi.
Hello. Very nice talk.
Thank you.
So I have a question on the example with the files.
Yes. Let me go back here.
So to what I understand, since you have multiple multi-shot continuations,
yes.
The suspend runs once, but the resume can run multiple times, right?
On suspend runs multiple times.
Yes. So
it's well bracketed. For every time you close it, you open it again on resume.
But if you have a handler such as flip, then would the resume runs twice for every time suspend runs once?
No, suspend is also executed twice. Oh yeah, of course. But I'm happy to discuss this offline.
Okay.
Yeah.
Yeah.
let's take the speaker. Okay, so the next talk is about the semantics for React hooks, and the presenter is Jay Lee from Seoul National University.
Cool. Good afternoon. I'm Jay Lee, a master's student from Seoul National University, and I'm excited to present React Trace, a semantics for understanding React hooks. This is a joint work with my colleague Jung-won An and my advisor, Professor Kwang Keun Lee. So today, React is the go-to framework for building web applications. In a recent Stack Overflow developer survey, about half of the developers said they use React. So please raise your hand if you've ever used React before. Awesome, that's quite a few. But for those who are not familiar, what is React? Let's say you want to build a simple counter. When user clicks the button, the number should be incremented by 1. In traditional imperative UI programming, you need to update an internal state and then manually update the UI after the state gets updated. And as the UI gets more complex, it's easy to create a UI bug where the state and the UI get out of sync. So React frees the developers from this burden by automatically updating the UI when the state gets updated. So in React, we divide and conquer the UI into a view hierarchy to be rendered on the screen. So for us programmers, this allows us to compose smaller views to build a rich UI. And for React, this enables the runtime to efficiently update only part of the UI when the state updates. And a component is a specification of a view that describes how it should look and behave. And component is simply a JavaScript function. So what does it look like? Here's a simple recursive component called bin, short for binary tree, which will be rendered as 2 to n dots on the screen. Like bin, all components should be fully declarative. And as a manual for a view, React runs the component to read it. But a mere act of reading a manual shouldn't trigger a side effect. I mean, if reading the manual for your fridge opened the fridge door, you'll get surprised, right? It's the same for React. React expects the component function to be free of side effects. But any non-trivial UI needs to be able to interact with the user, which is inherently effectful. So React provides a controlled way to declare side effects through React hooks. So we focus here on 2 fundamental hooks, useState and useEffect. useState manages component state. So it takes initial value as input and then returns the current value in the setter function. And useEffect runs the provided closure called an effect after each render. But here's the problem. The semantics of React is quite tricky and subtle. So a component is like a spork, a single function playing two related but distinct rules. So initially, React calls a component to construct a new view. This is used to render the view for the first time. And subsequently, the same component is called, possibly with a different argument, to update an existing view. This dual nature can be confusing because the same function behaves differently based on the component lifecycle. So here's a counter component to illustrate this. So when first called, useState uses the provided argument x to initialize the state s. And when user clicks the button, it triggers a re-render, causing React to call the counter again. But this time, useState performs a completely different task of returning the previous state value. And as a side note, you can simply update a JavaScript variable s to update a state, even if it weren't a const. So all updates should go through the setter function setS. And there are certain rules to follow when using hooks, collectively known as the rules of React. For example, hooks must be called unconditionally at the top level of a component. So this con component here violates this issue by calling useState conditionally inside an if branch. So when you click show, con will re-render and crash the UI. This is because React identifies a hook by its internal position in a linked list, and conditional hook calls violate this assumption. So while React imposes multiple rules and disciplines to make this clever machinery work, providing the abstraction of a quote-unquote declarative functional components, it is still a DSL embedded in a freewheeling language of JavaScript. And this inevitably makes React a leaky abstraction, puzzling many developers. And it's not just me saying this. The most visited question with the React hook tags on Stack Overflow asks about this use state semantics. So now a quick quiz time. This is a code snippet distilled from those questions. And note that we're using an ML-like syntax used in our paper. So obviously when the counter is first called, it prints counter followed by, wait a second, my magic wand. It first called counter followed by return. But what will be the order of the printed strings after the button is clicked? Do you think it's update, counter return? Or will it be B, counter return and update? Or will it be C, counter update and return? So if you think it's A, please raise your hand. Okay, there's one. If you think it's B, please raise your hand. Okay, I see 2. If you think it's C, please raise your hand. Okay, I see quite a few. So the answer is C, counter update return. So as you can see, hook semantics can be quite subtle even for us PL researchers. And a common pitfall when using use state and use effect together is the infinite render loop bug. So there are over 1,600 questions on Stack Overflow asking about use effect and infinite. So the inf component here demonstrates this issue. So the effect provided to the use effect hook runs after each render and calls the setter function. So this makes React check whether the state has changed, and if it has, it's gonna invoke inf again. And since the setter function here always updates the state to a new one, this triggers another render followed by the effect call, which creates an infinite loop. So as a result, the UI keeps rendering an ever-increasing stream of numbers. Another common source of confusion is a different kind of infinite render loop bug, caused by directly calling the setter function inside the component body. So the most visited question tagged with React.js and infinite loop on Stack Overflow asks about this very issue. So let's take a look at the inf2 component here. So here the setter function is provided with an identity function, meaning that the state doesn't change. But regardless of that, a setter call inside the component body is hardwired in the runtime to trigger another check by re-executing the component body. So this time, unlike the previous issue, this view never even reaches the screen. So the runtime keeps trying infinitely to read the component body. So to explain and precisely understand these issues, we need to be able to reason about the render semantics of hooks. So we present React Trace, a semantics that clarifies the behavior of React hooks. So seeing is believing, so here's a React Trace interpreter and a visualizer we built based on the formal operational semantics. So our visualizer lets users inspect how their program renders step by step, alongside the visualization of the view hierarchy. And you can use the slider to replay the entire execution. And our tool is available online at react-trace.vercel.app. And here's a glimpse of our semantics, which formalizes the React machinery. And don't worry, you don't have to squint. I've made it intentionally small. So we model the React event loop using a small step semantics of transitions of configurations. And we also, invoking the component body is modeled in a big step style, shown on the bottom left. And on the right is the diagram illustrating all the semantic functions and their dependencies, with enclosing boxes depicting the required contexts. So please read our paper for the full details. So does React Trace really model React? And the answer is yes. We built a conformance test suite with 38 tests covering 18 scenarios. So these scenarios include edge cases of React. For example, scenario 18, where a child tries to update parent state during evaluation, which correctly results in an error. Moreover, React Trace does not target a specific version of React. So we validated it against all major versions, including version 16.8 when hooks were first introduced, all the way through 19.1, which was released earlier this March. And all tests passed except for one minor optimization difference in scenario 17, where the order of the prints slightly differ due to the runtime optimization in React. But this is not a defect in our semantics. We could have included this optimization in our React trace, but we deliberately chose not to keep the core semantics clean. In fact, we went further and proved in our paper that our semantics matches the optimized one when the components are side effect free. And talking about theorems, we have 2 conformance theorems about React. So we extracted 2 key properties of React hooks from the official documentation and show that React trace precisely captures both of the properties. So theorem 1 explains the second infinite range loop issue we saw earlier. So a call to a setter function during the evaluation of the component body immediately leads to its re-evaluation. And the second theorem describes the mechanism behind the first infinite range loop issue. If use effects are executed after a re-render triggered by itself or by one of its ancestors updating their state. So React Trace opens several exciting research directions. First, a semantic-based static analysis and type systems that go beyond current linters. And second, our semantics can serve as a foundation for reasoning about optimizations, including the ones included in the recent experimental React compiler, and also different rendering strategies such as server-side components. And third, we can refine the semantics for pedagogical purposes to help developers build correct mental models of hooks. And last but not least, we can integrate it, use it with existing web semantics for end-to-end verification of web programs. So here are the key takeaways. React Trace is the first form of semantics for React hooks, validated against real React, providing both a foundation for reasoning about React applications and a basis for future tools. So don't forget to check our online visualizer and bookmark our GitHub repo. And I'm also applying for PhD programs this year, so let's talk if you're interested. Thank you.
Thanks for a great talk. Say questions?
Hi, quick question. Nice talk, and do you see anything in this thing that can be applied to other web frameworks like Vue.js or Angular or Svelte or something, or even like Flutter?
Yeah. This is actually, maybe it's an obscure web framework but it's a web framework called Dioxys in Rust. And as you can see, it looks quite similar, right? So we have a discussion in our paper how this can be extended to other frameworks, including something like Dioxys in Rust or like Svelte or other web frameworks. Interestingly, there is something called rules of hooks also in Dioxys. So I think our approach can be applied to other frameworks as well.
Thank you. I'll check out.
Thank you.
Other questions? So you used 35 test cases to verify the semantics?
Yeah,
is
38 test cases.
38 tests. So is it sufficient to prove the equivalence?
Well, yeah, you can. Yeah, it may seem insufficient, but that's why we have these conformance theorems. So we have theoretical proofs that our model reflects the official React implementation as they describe in their documentation.
Okay.
So you said this works. You gave some examples with some hooks. Does this work for all hooks?
Yeah. Well, our model currently models use state and use effect, and we have a sketch how we can extend this model to other hooks as well. Okay. We designed this to be extensible, so I hope it's going to be straightforward to extend to other hooks, as we've included discussion in our paper.
Okay,
yeah.
Thanks.
Thank you.
Okay, so let's thank the speaker.
Good talk. Cool. Can people hear me?
Yes.
Awesome. Okay, thanks. My computer insists that it's midnight, so good evening, everyone. So I'm Sean Nagy. I'm from UCSD. And basically, the people listed on the slide and a few others of my collaborators have been thinking for a while about this problem of proving properties that hold over infinite collections of programs. And so we've tried a number of different ways of proving these kinds of properties, and I'll explain more about this in the talk. And we found that it's actually very, very difficult to design a precise verification technique. And so after a while of struggling with this, we started to think that maybe we weren't the problem, maybe the problem domain was the problem. So we started digging into the theory and trying to construct semantics, and we found some really interesting hardness results that I want to talk to you about here. Before I get to that, though, I should probably motivate what this problem is and why we care. So because LLMs are very popular, we'll use an LLM as our motivating example. So suppose you go to ChatGPT and you say, hey, give me a function that computes factorial. It says, OK, great, I know how to do that. I'll say, here's this function, compute factorial. I'll handle the base case first. If n equals 0, return 0. And you're watching the LLM print this out, and you realize, wait a minute, that's already wrong. 0 factorial is, in fact, not 0. It's 1. So no matter what the LLM does at this point, right, it can try to generate very reasonable-looking programs, but it's always going to be wrong. So what you would ideally want is to be able to say at this point, before it generates anything after this return 0, to say, hey, you made a mistake. Let's backtrack or resample or do something else. Let's not waste our time here. So if we think about sort of abstracting away, what is this problem? Well, this prefix here, this string, really defines a set of possible programs, right? And so each of these programs is some continuation of the string that the LLM generated. And maybe you could think of this as being defined instead of by some weird picture as by a grammar. And then we'd like to prove, in the context of our example, the property that no program in this set computes 0 factorial correctly. So if I give the input 0, every program in this set will return something that's not 1. And so, like I said, this has some applications in LLM-based code generation. And we have a paper conditionally accepted at POPL that kind of gives you a programmable framework for doing these kinds of things in that setting. But it's also useful in classical program synthesis and certain kinds of verification when you have dynamically loaded code. So this is kind of our problem. Fix this general problem setting in your head. And like I said, we've been thinking about how to verify these kinds of properties for a long time. But we eventually realized that we should try to walk before we tried to run. And so we started thinking about, OK, going back to nuts and bolts, how can we define semantics for sets of programs? Right. So this is hopefully a pretty familiar collecting semantics for individual programs. Here, S is a single program. And the denotation of S is just a function that takes in a set of input states like P, and then returns the set of states that you can reach by running S on input states in P. So this is pretty familiar. I'll call this a single execution semantics for reasons that'll become obvious towards the end of the talk. Now, if I have some set of, for example, maybe 1, 2, 3 programs, then it's pretty reasonable for me to define a semantics of a set of programs as just a function that takes in a set of input states and then returns the set of states that are reachable by running any program in the set. Right. So this seems very rational. And so you can define a semantics in this sort of a way. We call this, like I said, the single execution semantics. And then you might try to build verification techniques on top of that semantics. And if you do, you'll get something roughly similar to what we have in previous work, where we've built out a program logic and proof synthesizer and all this neat stuff for this. But there's a bit of a problem. I'm not going to end the talk 4 minutes in. The problem is that you actually can't reason precisely about loops over this semantics. So for a while, we thought that this logic that we developed, which was relatively incomplete if you allow your sets of programs to include loops, we thought that that was an issue on our end with not being able to come up with precise enough while rules. But it turns out that it's actually an issue with this semantics. So now I'll explain to you why. If this gets a little technical, don't worry. I'll kind of resurface in a couple of slides. So there's this nice property that we are hopefully like pretty familiar with called compositionality. So here, S1 is a set of statements, and so is S2. And then S1 semicolon S2 means that I'm describing the set of all programs where I take something from S1 semicolon something from S2. So that's the syntax that I'm using here. So compositionality over this semicolon, for example, means that I can figure out the semantics of my subcomponents, S1 and S2, and then I can use those together to determine the semantics of S1 semicolon S2. Right. And this is a property that we all love to have, because when you have this, you can do sort of like modular analyses. You can analyze each component of your term, and then you can fuse them together to get the like some analysis result on your whole term. And things like work really nicely when you have this kind of property. And you might hope, right, that we can do something similar for all the other constructors in like some simple language. And for while loops in particular, we'd really like to be able to somehow, if I know the semantics of B and I know the semantics of S, I should be able to combine them and figure out the semantics of while B do S, right? And if I can do that, then I can do some sort of nice compositional reasoning over loops. So it turns out that with the way that we've defined semantics, actually you can't do that. There's no way to go from the semantics of B and the semantics of S and derive from them the semantics of while B do S. So in this case, we have this really ugly property called non-compositionality, which means that if you try to build analyses on top of this semantics, they're either going to be like sort of inherently imprecise, or you'll have to do something that steps outside of this sort of like modular compositional style of program analysis, which would make everyone very sad. So now we're going to talk about why this is non-compositional. And the sort of like key thing, if you don't understand the next couple of slides, is just that the semantics is too weak. So the information about the semantics of B and semantics of S just isn't enough to tell us what the semantics of the set of loops is. But now I'll explain what that means. So let's kind of consider while B do S, and imagine maybe this is one of the loops in while B do S. While x is not equal to 1, do x plus plus. And we're going to just step through evaluating this loop on a really simple example to understand what kinds of information we need to know about the guard in order to figure out how this loop will run. Right. So we run the loop on x equals 0. First, we check the guard, and we see that it evaluates to true. So we run one iteration of the loop. Now we're at x equals 1. We check the guard again. We run. We don't run the body of the loop, right? So we finish. And so what we needed to know about the guard in order to figure out that this execution was possible was that the guard was true on x equals 0, and the guard was false on x equals 1. Right. So sort of if I abstract away the guard and I had some set of guards B, I would need to know that there existed some guard in my initial set of guards that had those two properties. Now if I think about maybe my set B is this setup here, and I want to know, can I determine like this kind of a property down here from just the semantics of the set? Well, first I would ask what is possible for programs in this set to do on x equals 0. And so, for example, on x equals 0, my semantics will tell me that some guard in the set will give me true, and some guard in the set will give me false. Okay, so now I know that there's some program in that set that will evaluate to true on x equals 0. And I can ask my semantics again, hey, what happens if I run one of these guys on x equal 1, and it'll tell me I can get something, some of them will give me true and some of them will give me false. So I know that there exists some guard that will give me false when I evaluate it on a state where x equals 1. But the problem is that this formula on the bottom doesn't imply the formula just above it, because I know that there exists a guard that satisfies the first property and there exists a guard that satisfies the second property, but I don't know that there exists a guard that satisfies both of these properties. So for example, I could change the set of guards in the upper right. Instead of equals equals 1 and not equals 1, I could change it to 2. And then the semantics is exactly the same, because for any start state, I can get true from one of the guards and false from the other guard, right? And so this like fact along the bottom is still true. But then the sort of witnesses to like this existentially quantified formula here and that one over there are different guards. So there actually is not any loop that uses one of these guards that gives me this sort of like execution pattern. So zooming out a bit, right, I can say that the semantics of those two sets of guards is equal, and the semantics of x++ is obviously equal to itself. And these two statements tell me that on any single input, the guards and the bodies will behave like roughly the same. They're roughly indistinguishable if I just like pluck one out and run it once. But if I consider the set of loops which have body x++ and differ in the set of guards that they use, I'll see that the semantics are not equal. And the point is that when I execute over several loop iterations, I'm running the guards multiple times. And because I'm running them multiple times, I can start to see that actually they don't have the same kinds of behaviors. So the picture that we end up in is something like this, to bring things back up to a slightly higher level, where we have this single execution semantics and corresponding notions of verification when we don't allow loops in our sets of programs. But now we need some kind of semantics for when we do allow loops, and we'll correspondingly have some notion of verification. So the trick ends up being to basically lift our semantics to operate, instead of on sets of states, to operate over sets of lists of states, right? So I'll kind of like blast through this illustration a little bit. So the idea then is that P becomes a collection of like lists of states. So that's a list of length 1, and that's a list of length 2. And when I run a program on a list of states, I get a list of outputs, right? And now I can take, for example, just a state that can, a set that contains just the list x equals 0, x equals 1, and I can run it on that first set of guards from earlier. And I can see that it's possible for me to find a guard that gives false on x equals 0 and true on x equals 1. And then it's also possible for me to get a guard that gives true on x equals 0 and false on x equals 1, which is sort of the behavior that we needed to establish what was going on with the loop that we saw earlier. In contrast, if I look at the set x equals 2 and x is not equal to 2, I get completely different outputs, right? So now the semantics of these things are completely distinct. And it turns out, and you'll see if you read the paper, that this semantics is in fact compositional for loops as well. And so you can kind of push this through and get some reasonable extension to our logic, and then you get like a relatively complete verification system. Since I'm running out of time, I'll be a little bit fast with the next couple slides. But basically in the paper, you can read it, and we prove that this multi-execution semantics is actually the minimal extension of the single execution semantics that gives you compositionality over loops. Second, we can prove that the properties that you can prove in our logic are equivalent to the semantics on the left. And so as a result of those two facts, you get that this like logic that we develop is sort of a minimal extension of our original one. So that's what I've got for you today. There's a bit more in the paper about how to reason about divergence and some other things. But I hope you guys found that interesting, learned something useful, and I'm ready to take questions.
Okay, so any questions?
So the new semantics is a power set on the list of states. How do you decide the length of the list, or you have to use all lengths?
Yeah. So you basically like this you can think of maybe as a predicate on lists of unbounded length. So one property that I might like to ask, right, is like, generally the kinds of properties that you would need to write are not for a fixed length of list. They're for lists of unbounded length. Yeah, so I might need to ask, like, does there exist a list that represents the execution of a loop, which like eventually will terminate, or will eventually like give me some good output state? Oh.
Okay, thank you.
Yeah, thanks for the question.
Okay, thank you. So let's thank the speaker. Okay, so the last talk of this session is about zero overhead lexical effect handlers.
All right.
And the speaker is Kong Ma from University of Waterloo.
Hey, my name is Kong from University of Waterloo. Today I'm going to show you our latest work on the compilation of lexical effect handlers. In particular, I will show you a novel compilation technique that makes lexical effect handlers zero overhead. You will see what I mean shortly. First, some background for our work. Effect handler is a powerful language feature that allows programmers to write programs with interesting control flows. It subsumes many popular language constructs like async await, coroutine, and generators. Effect handler, though powerful, suffered from a modularity problem. Here's an example. Assuming you are an application developer, you import a plugin and a framework from third-party libraries, and you invoke framework by instantiating the plugin. Now, say you want to monitor the usage of plugin by the framework. You create a wrapper function that calls plugin and raise the login effect, and you also install a login handler in your application. Programmers expect this to work because both the raise site and handle with expression use the same name login. They would expect them to refer to the same thing. However, many works on effect handlers use a semantics based on dynamic scoping. When an effect is raised, it is handled by the closest enclosing handler on the stack. To see how such semantics could go wrong, let's assume that the framework that you imported installed a handler for its own purpose. Of course, as the application developer, you do not know that. If you run this program, the login effect raised from plugin will be accidentally handled by the handler in the framework. This behavior makes it very difficult to reason about the program. For example, if you import a framework that does not install an enclosing login handler, then your application will work as expected. We know that this problem is similar to the modularity problem with dynamically scoped variables, which have fallen out of favor since the 80s. Recent work has proposed lexical effect handlers as a promising alternative. In a language with lexical handlers, the handle with expression introduces a variable binding. When a lexical effect handler is installed, the runtime generates a fresh name for this handler. This name substitutes for the variable inside the handled body, and it is passed down the call stack, eventually reaching the call site. Besides, names are values that can be captured by the closures. Because the raise site is precise about which handler it raised to, the problem of accidental handling is avoided. Here's another presentation for the same expression, which highlights the stack structure. The program has two stack frames, a handler frame at the top with name 314, followed by the current redux. This slide compares the handler with lexical and traditional semantics. We can see that with lexical semantics, every handler is given a globally unique name when it is installed. The traditional semantics does not have such guarantees. Prior work have also shown formally that programs built with lexical effect handlers enjoy modularity. However, when compared to the traditional handler semantics, the lexical handler semantics has a performance disadvantage in that every function needs to explicitly receive handler arguments. The passing and receiving of the extra arguments impose a runtime cost, even for rarely raised effect, such as exceptions. And we are concerned that even though lexical handlers has nice theoretical properties, language designers might still shy away from them because of this overhead. Generations of language designers have advocated for zero overhead principle for exception handlers. This idea is best described by the quote from Bjorn Strostrup: "What you don't use, you don't pay for." Zero Lexa is our attempt at achieving this goal, making Lexa the first language to have zero overhead lexical effect handlers. In the next few slides, I will demonstrate the technique by walking over two examples. We will first see a non-zero overhead execution, which is the state of the world now, and then we will figure out how to make the execution zero overhead. Here's the first example. I show the program on the left and a stack diagram on the right. Please only pay attention to the diagram on the right. Now, as the program runs, function main install a handler, which is given the address 5. This address acts as the name of the handler and will be passed down the stack. This address, okay, now the next, the main calls foo by instantiating foo's handler parameter with this handler. The black box here denotes a handler parameter binder, and the arrow denotes the parameter instantiation. Inside the function foo, it installs another handler, which is given address 6. It then calls bar by instantiating the two handler parameters. Finally, bar raises to handler at address 5, which transfers the control to the stack address 5. Similar things happens when bar raises to handler at address 6. Now let's ask ourselves, can we locate the intended handler without passing down addresses? The key observation is that handler provenances, which are represented by the arrows, are known statically. Even if we don't explicitly pass down the addresses, we still have a way to know where the handler passing originates. We can just trace back the static provenance information and find the intended handler. Let's see in action how handlers are located in zero laxa. When an effect is raised, the control goes to a runtime stack worker. The stack worker carries a state called clue. It is a single integer denoting the de Bruijn index of the handler variable responsible for the raised effect. In this example, the clue is initialized to 0, which is the de Bruijn index of handler parameter h2. The stack worker walks up the stack. At each call site, it transitions the clue according to how the parameter is instantiated. In this case, h2 was instantiated by a local handler inside foo. Since this local handler's de Bruijn index is 0, the clue is updated to 0. Finally, while inside the foo, the stack worker finds a local handler with de Bruijn index 0. It thus successfully finds the handler. Zero laxa also works with higher order functions, which I'll demonstrate using a second example. Some of you might get lost in the next 2 minutes, or you might already get lost, but don't worry. The takeaway here is that the arrows on the diagrams are known statically, and the stack worker is simply following these arrows. Similar to the first example, this example has 3 functions, main, foo, and bar. Notice that bar is a first-class function that is defined inside the scope of 2 handlers. Also notice that foo is a higher order function that takes in effect parameter alpha and a term parameter g, where alpha stands for the effect that g raises. At the call set of foo, the effect parameter is instantiated with log and exception, representing the handlers that the term argument can raise to. Now, assuming that we are at a point on the right, main calls foo, foo calls bar, and bar is about to raise to handler log. We start stack working with an initial clue infinity. We use infinity to denote handler variables bound outside the scope of the immediately enclosing function. And in this case, log is bound outside the function bar. From another perspective, log is captured by the function bar. Furthermore, the clue contains an extra field to record the effect name. This information will be used to disambiguate a fork on the provenance path, which you can already see on the diagram. When a stack worker arrives at the call site of bar, it attributes the effect to alpha, which represents the set of handlers captured by bar. Since alpha's de Bruijn index is 0, the clue is transitioned to 0. Next, the stack worker reaches the next call site. The clue attributes the effect to alpha, but alpha is instantiated with 2 handler variables, one for handling exception and one for handling logging. The second field of clue now plays a role in disambiguating this fork. Because the variable log has a matching effect name logging, this variable is chosen. And the clue is updated to carry the de Bruijn index of log, which is 0. Finally, the stack worker finds the local handler with de Bruijn index 0 inside main, and with that, we've successfully located the target handler. Now let's see what the compiler does to realize the stack working and clue transition. The first stage of compilation involves compiling a source language with handler passing into a target language without handler passing, but each call site is now annotated with a metadata. This metadata, encoded in de Bruijn indexes, records how the handler parameters would have been instantiated. In other words, the call set metadata keep track of the handler provenances. Next, the target language, now without any handler passing, is further compiled to binary, as is shown. And the call set metadata that record handler provenances are compiled to a static lookup table in a data segment in the binary. They can be efficiently looked up using the return address of the function call. Notice that 0lexa doesn't instrument extra code in the binary. The stack worker only consults the metadata when an effect is raised, so the cost is entirely off the mainline execution path. Furthermore, we proved that the translation from the source to target language is semantic preserving using a simulation argument shown. This result implies that the handler found by the stack worker is exactly the handler that would have been used if the handler was passed down explicitly. We integrate zero overhead technique into the existing Lexa compiler. Programmers can write Lexa code and declare some effect to be exceptional. The Lexa will compile exceptional effect handlers using zero overhead technique, while compiling other handlers using handler passing. Now, for the first part of evaluation, we ask whether zero overhead implementation is really useful. We hypothesize that exceptional handlers that are rarely used would benefit from the zero overhead implementation. We carry out a simple case study where coroutines cooperatively yield control to each other. On the graph, the x-axis denotes how often yield happens, and the y-axis is the time to finish the tasks. The larger the x-axis, the less frequent coroutine yield to each other. The graph indicates that when the x-axis is small, which means that yield happens frequently, the performance of zero overhead technique is bad due to the cost of frequent stack walking. However, as x-axis moves to right, yield happens infrequently, and zero overhead starts to have a performance advantage. We compare the performance of zero overhead technique with handler passing using benchmarks that use effect infrequently. These programs mostly use exception handlers to defend against unusual conditions, which actually never happen during the execution. Because the zero overhead compilation avoids overhead of handler passing, we see a clear performance gain for these programs. In conclusion, we hope that lexical effect handlers, now armed with this zero overhead technology, would appear more appealing to future language designers. Thank you for your attention.
Hey, very nice talk. So the cost that you remove is the costs of me having to pass down explicitly the parameters, right? It's not the runtime cost.
It is runtime cost because with lexical effect handlers, you need to pass down the handlers. You need to pass down names, for the function to raise to that to the handler. So you need to pay some cost at the runtime.
But if I pass a parameter, couldn't the compiler figure out that I just pass a function address?
Sorry, say it again?
If I pass a parameter, then how is it different than just the compiler figuring out that I need to pass a function pointer?
Yeah, you mean the compiler could figure it out sometimes, but say that you are using separate compilation or you're doing modular development, right? In this case, the compiler don't have global knowledge to do this kind of optimization, so it has to be passed on explicitly.
Okay, thank you.
Thank you.
Hey, cool work. So you have these two different implementations, right?
Yes.
The one that seems to work really well for if you use effects a lot, and the other one when you use them rarely. Do you also incorporate, or maybe already, like caching the information so that only the first time you use the stack walker, then cache the address so you can just switch to the faster one?
That's a very good point. I see what you...
Because then you only pay once, right?
Right. We did not implement that, but I can see it working, yes. Yeah. That's a very good point.
Okay.
Thank you.
Hi, thanks for the talk. Could you go back to the second example?
Okay.
Thanks. So what happens if we just have let bar in bar, then we return the function that captures the effects? How do you prevent them from escaping the lexical boundary?
Sorry, can you repeat that?
What if we have the program let bar in bar? So
let bar in bar.
Yeah.
Okay.
Yeah. Then we are returning the function that closes over log and the exception effect?
Oh, that's a good question. Basically, the source language have a type system that will prevent any function that captures handlers to escape the scope of handlers.
So you're keeping track of the captures?
Yes, yes.
Okay.
So something that I did not present here is that we have a type system that helps this compilation.
Okay.
So yeah,
Thank
this
you.
type system will prevent this from happening.
Okay, thank you.
Thank you.
Okay, so let's thank the speaker.
Hello, welcome everybody to our session on debugging and validation. The very first talk is going to be by Elizabeth, and she is going to talk about debugging WebAssembly. As with all the sessions, we are trying to be very strict, 15 minutes, and then have a quick switch over. Yeah, and it's almost exactly 4, so please, Elizabeth.
Cool. Hi everyone, as you said, I'm Elizabeth. I'm going to be talking about if you're debugging WebAssembly, you might want to try putting some WAM on it because it might be helpful for you. So first let's dig into some background. Can y'all see that well? Huh, okay.
It's not very bright.
Yeah, is there a way to make this brighter? I don't know. Well, I'm going to just keep going. I don't know what controls that, but I'll just keep going. All right, so at a high level, I'm sure a lot of people in this room know what instrumentation is, but just in case anyone is unsure, instrumentation is at a high level injecting some logic to perform some operation, and it's really intentionally a generic definition. This is primarily used for application observability. And there are a lot of different strategies to instrument code. And what it boils down to is thinking through these different things to decide how you want to. Oh, yeah, it changed. That's awesome. Wait, what? Yeah, how you want to instrument your code. So thinking through the observable events that you need in order for your tool to actually function and run. You have to think about your how much performance will be hit by your, oh my gosh, this is throwing me off. How expensive it's going to be for your tool to run based off of the strategy that you've chosen. You have to think about portability. So the strategy that I've chosen, who will be able to use my tool? Does it work for my domain? And then the possibility of changing your application behavior when you don't want to. And all of these decisions lead to tooling fragmentation across different languages and across different environments. So if you're wanting your tool to run in a new domain, sometimes or oftentimes you have to re-implement completely. But what if we could write a tool one time and it ports by design with comparable performance across these different domains? So enter WAM, and I don't mean the 80s band, I mean this instrumentation framework that we've built to hopefully reduce this ecosystem fragmentation. And we observe doing this in the WebAssembly ecosystem specifically because there are some compelling properties here to help us. For one, WebAssembly is a polyglot, and it's also a managed language, so it runs on top of a virtual machine. Since WASM is a polyglot, theoretically tools can be language agnostic, and we haven't quite reached like this interoperability dream, but as things kind of improve here, we can have this really cool theoretical idea of building out this language agnostic platform for tooling. WebAssembly also being a managed language means that tools are portable across machines, so you don't have to write something specific to some architecture you're running on. And then you also have the possibility of having your engine itself managing your instrumentation. So how do I write a tool in this new framework? You have, let's look at this example monitor. This is a really dumbed down, like simpler version of doing a branch profiler where we specifically look at the BRIF opcode. So we're specifically profiling the different branches that are taken by some BRIF. So you can see the most taken branch, so you can kind of think through like possible compiler optimizations. So at a high level, this is what it looks like. If you know dtrace, it looks similar to that language. It's kind of inspired by AOP. So at a high level, we have our global state. So over time, we're accruing information on what branches were taken by this BRIF opcode in this map. You have where to match. So I want you to find all of the BRIFs that exist, all the BRIF WebAssembly opcodes. I want to inject this logic before the BRIFs that you find. And then if you want to, you can further constrain on the matches. So specifically, this is constraining to only matching on the BRIFs that you find inside the function with the ID number 25. And then you have the logic to run. So this is looking at the top of stack and then incrementing that taken branch by 1. So now we have this tool that we've expressed, this really short branch profiler for BRF opcodes. How would you apply this tool in the WAM framework? So you have this high-level architecture where you have this application you want to instrument. You have the tool that you want to apply to your application where you've expressed your instrumentation in terms of this DSL I just showed you. And I didn't show where it can use libraries in this example, but if you need to have more complex tooling logic, we offload that to some general purpose language that compiles to WebAssembly, and then you can call into this complex tooling logic in your script. So then we have the DSL compiler, and this is where it does this instrumentation for us. We have 2 different targets, and we can either target dynamic instrumentation with the WAM engine interface, also known as WAY. And when it does this, you'll note that the program itself is not an input to the compiler. And that's because it generates this program agnostic representation of the monitor. And so this tool.wasm output is compiling the script down to WebAssembly. And then there's some extra metadata that's encoded inside this module to instruct the engine on where I want to match and what I want to insert at these match locations dynamically. So when I actually have my application that I'm wanting to apply this to, the engine will see the different probes that exist inside this tool and then dynamically insert to my application and then run my now instrumented program. And this is really nice in a lot of different ways. So we have high observability because you can observe bytecode level or engine level events here. You also have high performance because of some optimizations I'm going to talk about in a bit. And there's no intrusiveness risk because the engine itself is managing your instrumentation rather than mixing it all into the same bytecode. And then we have high portability because this tool can now port across engines and then be applied to any program. But it's only portable across the WAY interface. So the only engine that implements this interface right now is Wizard, but we're hoping to standardize this for future engines so we can have this shipped monitor across engines, which would be pretty awesome. But for now, we have this bytecode rewriting fallback, so you can apply the same monitor through this alternate DSL backend, which is bytecode rewriting. So with bytecode rewriting, it literally just takes your application and mixes your instrumentation code into the application itself. So it's this red plus green module. So since it's just instrumenting WASM with more WASM, it can run on any engine. So it's highly portable. But when you do this target, you do have some limited observability because you can only observe that which is visible in the bytecode level. High performance because you inject inline at the locations you're wanting to instrument. There's a little more risk of intrusiveness, which I can dive into if people want to talk about this offline. And then you have high portability because it's just more WASM code and you're running it on an engine that runs WASM code. So yeah, high level, you write instrumentation once, the framework itself takes care of how you want to inject this, which will widen the domain that you're applicable in for your tool. So let's look at the engine interface. We have this tool.wasm that we've compiled. It is targeting the WAY interface, and it has this extra metadata on how you want to apply this instrumentation. So it's requesting the engine to find all of these BRF opcodes, and then I need you to pass me this subset of application state on invocation of the probe callback. So the engine has found our locations that it wants to instrument, it's applied these probes, and then when it eventually reaches this place dynamically, it invokes these runtime calls in order to invoke and pass that information that's been requested. And what makes it fast is that at a high level, you have 2 things that make it fast. You have the fact that each probe callback explicitly requests the application state that it needs to run. So this can be optimized with intrinsics, both in the interpreter and JIT tiers. Because what this boils down to is just a static constant, the first immediate on the opcode, and a stack location. So the top of stack is what it needs to operate. And then since this is just WebAssembly code, you can use your engine to optimize it with these intrinsics, and you can go as far as inlining the probe into the probe site. So one of the optimizations that we've done is in the interpreter. We call this the trampoline optimization, and we avoid these expensive runtime calls by generating these machine code stubs that bundle the requested state and then invoke the probe callback and then continue back into the interpreted application code. And you can see how much time this is saved here. At a high level, just think about this like intuitively. You don't have to like dig into all of these different representations we have here, but the red is the unoptimized case. So it's interpreting the application. We have that expensive runtime call and then interpreting the tool. And then the orange jits the tool. So you can see that simply jitting the tool doesn't really save you that much time. And it's because the runtime call itself is what dominates the overhead. So removing that expensive runtime call saves us a ton of time, and then further optimizing by jitting the tool saves us even more. So you can see how powerful the optimization is in the interpreter. And then for making way fast in the JIT, we have the WASM to WASM optimization. So you can think about this as basically inlining that machine code trampoline at the probed location when you JIT the code. So we transfer, invoke, continue, and we save that expensive runtime call, and then you can go as far as inlining to where you don't have any calls anymore inside the JITted code. And this is really cool, because you can see how you have the unoptimized case where you're JITting the application code, you have that expensive runtime call, and then you interpret the tool in the red. Then you JIT the tool in orange. You don't really save that much again. Then you have the WASM to WASM call, WASM to WASM optimization. So you still keep that WASM call, but you remove the expensive runtime call. Then JIT the code, then inline. So you can see that you've really saved a lot of time by doing this inlining optimization. Like 61.3x down to 1.6x is pretty powerful. And we have a lot of future plans for this. I'm gonna kind of glaze over this, but we wanna like explore instrumenting non-WASM code with WASM code. We want to extend the DSL to be more expressive for a lot of different use cases. We wanna figure out how to standardize this engine interface as well to make this portable instrumentation port where you can ship your own instrumentation with your code, and then study more optimizations and more tiers in the engine. Yeah, so like this is what we're doing. If you're interested, please read the paper. Please reach out if you have questions, play around with the DSL. If you find issues or have use cases that you want, like reach out to me. Yeah, this is what we're doing. I can take questions now.
For questions, please use the microphone. And while you come up to the microphone, I have a question. So you said it's a kind of AOP-like. So how powerful is your point cut language?
So you're able to go down to, it has opcode level granularity. So right now it's going down to like the true low level for WASM point cuts. And then you can kind of abstract on top of that. So there are a couple of different events that you can instrument right now, but we're gonna extend them over time. So right now you can go down opcode by opcode. You can do function entry exit. You can do basic blocks. And then as we kind of start crawling up the stack and going closer up the source code, I'm hoping that we can have more like abstractions above that to make it more expressive for higher level analyses.
So one of the, you have a question? Go.
Hi, great work. Do you plan on supporting interop with JavaScript in the future? Because what would be really cool is if you could have like one tool where you could write your hooks for JavaScript and WebAssembly, because I don't think that exists yet.
I think that would be really cool. Like that's kind of where you would have to go up the level of abstractions to start looking at what your events would look like for non-WASM events. But the way that the DSL is structured, it's very, how do we go back to this? So like you could have something like JS colon something colon something. So the DSL itself, I think, can generalize to other types of events that aren't just WASM specific. That's why we started it with like this WASM keyword to make it more generalizable to like events like that.
Yeah, because I could imagine JS, WASM export call,
Yeah.
before call or something like that.
Yeah, it
and
would
that
be really
that
cool.
Would be, yeah.
Yeah.
Okay, thank you.
Mm-hmm.
Hi, thanks for the talk, really interesting. I'm doing quite similar work, and I found that sort of in the monitor codes, I sometimes would wish there was a more high-level API to access information that the VM would know, but through rewriting, you don't know. How do you work your way around designing this API then?
So you mean like information that's not knowable at the bytecode level, but knowable in the engine? Is that what you're asking?
Yeah.
So go ahead and get started. If there is like if you need that type of level of observability, then you would have to use like the engine interface, because you would need to interact with the engine somehow to get that type of reflection.
So the engine exclusive information, do you think it's valuable to also expose it through your interface?
So right now, there's not a standardized way to reflect in WebAssembly engines, but if that type of reflection was added to engines like as an interface, then you could use that in bytecode rewriting. But for right now, since we don't have standardized reflection, it would need to be something that we expose in way.
Okay. Thank you.
Yeah.
The universe of WebAssembly, because at our research lab at Ghent University, what we do is we look at advanced debugging techniques, and we build those on top of, or prototypes on top of WebAssembly. And the debugging technique that I'm going to present today is our multiverse debugger for I/O applications. And why did we make this debugger? Well, we were looking for I went too fast. We were looking for better debugging tooling for microcontrollers. There have been a few talks at OOPSLA and also at the WebAssembly workshop that talked about bugs on embedded devices and better debugging tools. So I think we can agree that debugging on embedded devices is hard and we need better tools. And it's especially hard when you're debugging I/O bugs. And I have a small program just to sort of crystallize what exactly is difficult about I/O bugs. This program reads a temperature sensor here, and if it gets too cold, it will turn on a blue warning light, and if it gets too hot, it will turn on a red light, and then if the temperature is just right, both of the LEDs will be turned off. Unfortunately, there's a small mistake in this program, and you will only find it when you have a very specific conditions met. You have to actually lower the temperature to cold enough so that the blue LED turns on. And then when you rise the temperature slowly to the right temperature, then you will actually notice that the blue LED stays on. And so to find this bug, you will have to kind of iterate multiple times over your program until you find the right conditions. And that's not easy. How would we debug this as an IoT developer? Well, usually on hardware. You might not believe me, you might think, I just use a simulator, but actually 74% of surveyed IoT developers in 2021 said that they do debug and test on hardware. And what does that look like? Well, how would you debug our example? Well, there was someone with a similar issue on GitHub. He had his device would get very cold, but some temperature sensor on his device would report 4,000 degrees Celsius. So there was clearly something wrong. And how did they debug that? Well, they used ice packs to cool down the device to sort of replicate this. From the reaction of the room, I think we can agree that this is not ideal. This sounds quite cumbersome if you have to get ice packs out of the freezer. Now, this GitHub issue is from 2017. You might think, surely things have improved. Alas, this is an issue from 2024, last year in November, from the Raspberry Pi Linux repository, and again they're using ice packs to cool down their Pi. So clearly something is missing here. And there's actually a second part of why this is hard. So We don't want to use iSpecs. It's hard to kind of get the right input conditions. But on the other hand, it's also often the case that once you see the wrong output, once your bug actually manifests in the output, you're already long past the point in your program where the bug occurred, where the root cause of the bug is. So you kind of want to go back to that point to actually learn something about your bug, but you can't just use reversible debugging. You can't just go backwards because your output won't magically reverse either. And so we also would like to be able to do that. To crystallize all of these problems, just have the 3 main challenges that we identify in our paper and we address with Mayo. And that is, firstly, we want to explore non-deterministic input in programs on microcontrollers. Secondly, we want to have that reversible debugging and keep the output consistent while we do so. And then, of course, we're still in the embedded environment. We want to do all of this on microcontrollers with very few resources. So that's an extra challenge. Now, there's actually room on my slide for a 4th challenge, and we gave ourselves kind of a 4th challenge. We want to do this all formally. We want to have our new debugging technique described formally and have some kind of correctness criteria. I will talk about that at the end of the presentation. I will now start with the first challenge and sort of work my way down. So to explore this non-deterministic input, we looked at multiverse debugging. Now, multiverse debugging is a technique that was first presented at ECOOP 2019, and it's specifically targeted at non-deterministic programs, specifically parallelism in this paper. And the idea behind multiverse debugging is that instead of just debugging one execution path of your program, you're actually going to debug all of the different or many of the different execution paths in your program, so you kind of get this multiverse graph, and you can debug all of those at once. Now, the previous works on multiverse debugging were on models, so this is a model of your program, and here now we want to debug on hardware with I/O, so we want to make that concrete, and specifically we implement this as a remote debugger on top of our Arduino virtual machine. It's a WebAssembly virtual machine that runs on microcontrollers, these kind of devices. So our debugger is just connects to this, and you have a nice front end. This is Mayo, a screenshot of Mayo. So this runs on your laptop while you actually debug the virtual machine on the microcontroller. And so because it's an online debugger, a remote debugger, you can step through your program and you will see that you get a nice tree on the right where you can see where in the multiverse you actually are right now, and you can see sort of the history of the inputs that you have explored before. Now, of course, if we want to explore different branches, we don't want to use iSpecs, so we added this mocking feature where we can actually override values of sensor values that we read. So we have our input primitives in the Arduino VM. They return some value from a sensor, but we can actually tell from Mayo that ignore that value and just use the one we want. Now, with all of this, we can already go through our multiverse tree, but we want to kind of not always restart our application when we want to explore a new branch. We just want to kind of go back and jump from one place to the other. So that's our second challenge. And what do we need for that? Well, we need our snapshots. And so this is the only part of the formalism I will show you, so don't be scared. We're going to keep it simple. There's only one thing really that you have to remember from our snapshots. They have a KM, that's actually just our WebAssembly state, so that's the state of our WebAssembly program in Arduino, and a compensating action R. And this compensating action R is used to reverse the effects of our output primitives. So with this, we can already in Mayo select another branch, like we do here. So we're in the bottom branch and we want to jump to the middle branch. Mayo will show you how we will traverse the tree, and then we can just press the jump button on the right and we will go to that place in the program. So this is this figure a bit blown up, so we can, if we have snapshots all along the way, we can go from this node K5 to this node, and so we will go back to the most common, the earliest common ancestor that we find, and then we just will replay the execution. And we can of course use our mocking here to replay the input primitives exactly the way we want in this branch, the way our history was recorded before. Okay, so this gives us exploration in multiverse debugging on an actual concrete runtime, and we have this, and our output is consistent, but we're not really doing this efficient yet. So this brings us to our third challenge. Microcontrollers have very few resources. So how do we do this efficiently? Well, we invented a sparse snapshotting strategy where we only snapshot after primitives. So here we have an output primitive, and so after that we will take a snapshot, and then we can just run our program, and then at the next primitive, which is also an output primitive, we will take a snapshot again. So our snapshot list will look a bit like this. We have kn and km, and then if we want to take a single step backwards, we simply have to pop our last snapshot off the snapshotting list and perform the compensating action from that snapshot. And then we can restore the WebAssembly state from the previous state. So then we're basically where we were before. In our previous snapshot, our action has been compensated, and we can just replay deterministically the rest of our program up to the point that we need. Why deterministically? Well, we take a snapshot at every primitive, both input and output, so we know there's no snapshots in this path, so there's no input or output primitives. We know that we can just execute the WebAssembly. Now, sort of to test that this actually is efficient, we wanted to check that, okay, taking less snapshots, does that actually have a big impact on the overhead? And when we take less snapshots, we're going to have to replay more instructions. Doesn't that have a negative impact? Doesn't that take too long? So the first thing we measured was we took snapshot at every instruction, and then also at every 5, every 10, every 50, and every 100 instructions. And we see that actually taking snapshot at every instruction is has huge overhead. Here it goes already over 80 times slower than taking no snapshots. It's actually so bad that I kind of have to zoom in to see the other part of my graph. So here you have the different intervals, 5, 10, 50, 100, and then taking no snapshots at the bottom. And so we actually see that this has a huge impact. And the programs that we were usually testing, we would have between 10 and 50 instructions, and in practice it was actually quite fast. You wouldn't notice much delay. And then we also tested, okay, if we have to re-execute more instructions, how much slowdown do we get? And actually we saw that there the impact is very small. We can execute thousands of instructions very fast, and there's actually very little slowdown for our debugger. Now, just really quickly about the formalism, because I have not that much time left. So we had this formalism, I kind of hinted at it already. We wanted to say something about the correctness of it. And we came up with two theorems, debugger soundness and debugger completeness. What is the basic idea is that you have your debugger semantics, and you want those to be, those to not interfere with the language semantics that you're debugging. So if you have a debugging session that starts at the start of your program to some debugging state, this is the first part here at the bottom, then you want to have the same, be able to find the same path in the actual language semantics, so in WebAssembly in this case. And so the reverse of that is the debugger completeness, where if you have a path in your WebAssembly from the start of your program, you want to also have a similar path in your debugger. Now, before I take questions, I just want to quickly say that both my co-authors are also here. They will continue working on multiverse debugging on WebAssembly. So if you have more questions after the session, please go talk to them. They're the perfect people to talk to. And please check out our source code. You can always leave an issue or a star on GitHub. Thank you.
Do we have one quick question for Tom?
Hi, this is Arjun from Carnegie Mellon. I'm wondering, so do you run this code interpreted, compiled?
Interpreted.
It's all interpreted?
Yeah, so
okay.
The Arduino virtual machine just interprets the WebAssembly bytecode.
Okay. Do you have like any ideas towards like compiled code? Is that like part of like in scope of the Arduino stuff?
So are you talking about JIT compiling or?
Ahead of time probably, because it's on a microcontroller. Right?
No, exactly. So no, We just compile WebAssembly and just give it to Arduino. You can compile Arduino to several platforms. So you can compile it with Arduino, but also with Zephyr or something. But there's nothing special that we do or any optimizations.
Okay, cool. Thanks.
All right, let's thank Tom one more time. And the next talk is by
Okay, thank you.
Okay, let's thank Lena again. The next talk is by Ru Jin, and he is going to talk about saving debugging time.
Excuse me. Okay, thank you. Hi everyone. Can I start? Okay. Still 1 minute, 1 minute until 4:45. I can start, right? Okay. Hi everyone. My name is Rixin. I'm a fourth-year PhD student from Purdue University. My advisor is Professor Tianyi Zhang. I'm excited to share our paper. Show me why it's correct, saving 1/3 of debugging time in program repair with interactive runtime comparison. Bug fixing is one of the most challenging tasks for developers. In a recent survey of 950 developers, 44% said it was their biggest pain point. Automated program repair, or APR, helps developers fix bugs by automatically generating patches that makes failing tests pass. However, developers are still skeptical about the quality of APR patches. They need to understand how the bug is fixed. And they need to validate whether a patch is overfitting and compare multiple patch candidates. And an overfitting patch may make all tests pass by chance, but it does not truly address the root cause of the bug. This happens because APR tools may generate too many patches, too many plausible patches. But developers quickly lose confidence if the first few turns out to be wrong. According to the recent surveys, when developers receive overfitting patches, their bug fixing success rate drops by 65%. On average, developers spend about 23 minutes manually investigating and comparing the generated patches before deciding which one is actually correct. This process is indeed very time-consuming. There are several approaches to address this challenge. Patch ranking and classification techniques try to prioritize patches that are more likely to be correct. And patch clustering methods group similar patches together so developers do not have to go through a long list of candidates. Instead, they only need to inspect one representative patch from each cluster. Interactive patch filtering allows developers to answer predefined questions to quickly eliminate obvious incorrect candidates. However, even with these approaches, developers still need to manually debug the program. They must answer the several critical questions before they can finally decide which patch is actually correct. For example, how do the incorrect runtime values originate from the buggy code and propagate to the test article? And how does a plausible patch change the program's runtime behavior to fix the root cause of the bug? Now, while the interactive patch filtering approach does ask developers questions to eliminate incorrect patches, the effectiveness is quite limited because there are only a few predefined questions, and for program execution traces, it only allows side-by-side comparisons of 2 patches at a time. So to bridge this gap, we propose a tool called iFix, an interactive tool that helps developers better understand the runtime behavior of auto-generated patches. The input to iFix is a buggy project, along with a list of plausible patches generated by APR techniques. Like prior work, we also need to reduce the number of patches that developers must inspect, but this is not where our main novelty lies. This approach is called patch clustering and sampling. It keeps the candidate set both small and diverse. And it ranks the patches to prioritize the most promising ones. Our main contribution is called runtime behavior comparison. It runs the fail test with each candidate patch applied and records the runtime values of related functions. It then aligns these results into tables to compare behaviors across patches. Unlike prior work like compares only 2 patches at a time side by side, it supports a comprehensive comparison among multiple patches. We have implemented this iFix as a VS Code extension. In the next few slides, I will introduce the 2 core techniques behind iFix. The goal of patch clustering and sampling approach is to help users navigate candidate patch space without feeling overwhelmed. iFix first performs hierarchical clustering to group similar patches together. For each cluster, it selects the centroid patch as the most representative one. Finally, for each representative, iFix ranks these patches to prioritize the correct patch. Building on the hierarchical clustering, we designed a new interactive widget. It lets users navigate the patch space and choose directions based on their preferences for each sample patch. When a sample patch looks promising but not fully correct, right, users can zoom in to explore similar patches within the same cluster. iFix recursively divides each cluster into smaller subclusters until there are no more than 5 patches remaining. When the patch looks completely wrong, users can reject it along with similar patches that are also likely to be incorrect. Now let's move on to the main contribution of this work, runtime behavior comparison. It helps developers understand how incorrect values propagate through the code and how different patches fix those values. This is made possible through several steps of code analysis. First, iFix performs a call graph analysis to trace the function calls from the failing test to the crash location. For example, in this bug, there are 3 layers of function calls. The buggy code in the innermost function eventually causes the test failure in the outermost function. Second, iFix performs a diffuse analysis to extract the runtime values related to the bug. Starting from the bug location, it captures the defined variables, use variables, method codes, and sub-expressions, tracing them all the way down to the failing function, to the failing test function. After that, iFix instruments the source code to log the relevant runtime values. It then creates multiple copies of the code and applies each sample patch separately. Finally, we collect the runtime values from all instrumented versions of the code and aggregate these values into a comparison table. In this table, the same variable at the same line is aligned in one row, and the values are grouped and color-coded for easy comparison, which will be elaborated later. Now let's walk through the user interface. It has 2 main parts. The first one is called interactive patch exploration, which should have been introduced before, and the second one is runtime comparison table. The user can divide into a cluster or similar patches by clicking on the button Explore Similar Patches. And for the table, iFix creates one runtime comparison table for each function in the call stack. For example, the first table shows the buggy function, the second one shows its caller, and the last one corresponds to the failing test. These tables can be collapsed or expanded by clicking on the titles. Inside each table, the buggy variables are shown in red, while the values produced by patches appear in different shades of green. For each row, the same color is used to highlight the identical runtime values produced by different patches. With iFix, developers no longer need to apply each patch, set breakpoints, and repeat the same process, same tracing and debugging process over and over again with different patches. Right? Instead, they can use the comparison table to see the key runtime values, the difference of the key runtime values, and they can identify the root cause of the bug and distinguish the behaviors of different patch candidates. For more details about iFix, please check out our demo video on YouTube. To evaluate the usability, we conducted a user study with 28 participants from both academia and industry. We randomly selected 4 bugs from Defects4j as the bug fixing tasks for our participants. Our baseline is a state-of-the-art tool called IMPAFER. It's an interactive patch filtering system. For the patches, we used a learning-based APR. We used the patches generated by a learning-based APR tool called Cure. Unfortunately, this work was started before APR was conquered by LLMs. We aim to answer 3 research questions. First, how effectively does iFix enhance patch validation performance? Second, how much does it boost developers' confidence in auto-generated patches? And third, how does iFix support programmers with different levels of expertise? We recruited 28 participants, including undergrad and grad students, software developers, and research scientists. Most of them have at least 1 year of programming and Java experience, and each participant worked on 3 out of 4 Defects4j bugs, and their tasks were divided into 3 debugging settings: manual inspection, using iFix, and using the baseline tool. For each bug-fixing task, participants receive a bug report and a list of candidate patches. Except for the manual debugging setting, they first receive a short tutorial video on how to use the tool. They were also given access to 2 IDEs, VS Code and Eclipse, to help with debugging. And they had 20 minutes to debug each of the programs and choose the correct patch they believe to be correct. After each task, they completed a short survey to share their experience and the feedback. Our results show that compared with manual debugging and the baseline, our tool increased the success rate by 40% and 8% respectively. It also reduced the debugging time by 36% and 33%. These improvements are statistically significant as confirmed by a one-way ANOVA test. According to the post-hack survey, using our tool made participants more confident in patch selection. The median confidence score increased by 50% compared to manual debugging and 20% compared to the baseline. And finally, as the programming expertise increases, the benefits of using iFix became even more significant. Due to time limit, I will only present the key findings here. You can visit our website for more details about the user study. So in addition to the qualitative user study, we conducted a quantitative evaluation to see how good the sampled patches are. We compared with 4 ranking baselines: original, static, learning-based, and similarity-based ranking. We also asked 2 more research questions. First, fourth, how effective is our clustering and sampling algorithm in prioritizing correct patches? And fifth, how sensitive it is to different APR techniques. In iFix, the ranking of a patch within a hierarchical cluster is determined by the position in the nested cluster architecture. For example, if a correct patch is ranked at index X in level K, and there are N1, N2, and so on clusters at each level along the path, the final rank of the patch is calculated as N1 plus N2 and etc. up to Nk-1 plus X. Our results show that this approach improves the ranking of correct patches and generalizes well across different APR tools. And this concludes my presentation. Thank you all for your listening, and now I'd like to open the floor to questions.
Hi, thanks for the talk. I'm curious how iFix behaves when the different patches result in very different call stacks. There may be very different sets of variables in scope that may have different numbers of frames. They may result in like loops with different numbers of iterations or recursive calls with different numbers of. How do you handle that?
Okay, so for loops, right? So for loops, we will aggregate different iterations of loops within one cell. So we only record the last iteration. And for recursive calls, now unfortunately we can only show every function calls, but it should be considered in future work, right?
And what if the call stack is just very different? I mean,
okay, for this,
different functions.
Yes. For this, we will display all call stack among the different patches, and for the patches that visit this function but not that function, so the runtime value will be blank. So the users will be able to distinguish the execution traces from the table.
Okay. Did that show up in the user study, or
I'm sorry?
Were there cases like that in the user study?
So for the user study cases, there are cases that the execution traces are different, but there are not different functions.
Okay.
Yes.
Okay, thank you.
Thank you.
Our speaker. Ryan, and he's going to talk about translation validation for LLVM's Arch64 backend.
Right. Thank you. I'm actually not Ryan. I'm Nuno. So this talk is about correctness of compiler backends. And so to make sure we are all on the same page, so here's how a traditional compiler looks like. So we have a bunch of front ends. They take some programming language, produce the same representation, some IR. The optimizations rewrite this IR, and then the backend takes this IR and produces assembly. And so here we are wondering, is the compiler backend correct or not? And so what's in a backend? So traditionally, backends were quite simple things. So we're like a one-to-one mapping between some IR instruction and some assembly instruction. But these days, backends do all sorts of optimizations. So they are a bit of a compiler on their own. Okay, so they're super complicated things. And so we should ask, are these compiler backends correct? And the answer is, well, of course not. And you can replace compiler backends with any big program, and the answer is always the same, smiley, right? The backends in LLVM in particular have more than 1 million lines of code. So of course, the number of bugs that you have, it's non-trivial. Let me give you a real bug that we found. So this is some LLVM IR snippet. So it loads a vector with 16 elements, 1 byte each. It changes one of these elements and then stores back the whole vector. Okay. Now, if you are a smart compiler like LLVM, you issue this ARM instruction that essentially stores directly 1 byte. So you change the vector in place instead of loading, updating, and storing back. The problem is this instruction can store anywhere in memory because the index is not validated. And so, if the index is out of bounds, you can store anywhere. And what the LLVM specification says roughly is that if the index is out of bounds, you should produce a Poisson tensor, a Poisson vector, which does not allow us to generate assembly that stores anywhere in memory. Okay, and so LLVM was clearly wrong. So this is a bug, and it actually introduced a security vulnerability in a compiled program. And we reported this bug, and now it's fixed. And so it was fixed using this AND instruction that clips the index, so it doesn't store anywhere in memory anymore. It can still change some arbitrary element of the vector, but this is a correct refinement of yielding Poisson. Okay, so we turn to translation validation, which is a way to certify that what's going on is correct. So, so this is in contrast with compiler verification, where we need to prove the correctness once and for all for the whole compiler. Translation validation is much simpler, which essentially you certify that this particular compilation was correct, but you cannot make any guarantee about compilation of other programs. And so Alive 2, kind of showed us in the past decade that you can make it practical. So Alive2 has already found like hundreds of bugs in LLVM. It's actually a mandatory tool now. So when you open a pull request with LLVM, you need to provide a proof using Alive2 to get the patch accepted. And so this kind of shows that this technique works. And so this paper is about applying translation validation now for backends. Because Alive2 focuses just on the IR optimizations. Now we go one level below. OK, so in a nutshell, ARMTV, which is our tool, so takes this LLVM IR as input. We use LLVM to produce ARM64 assembly. Goes to the lifter, which is the main contribution of this paper, which takes assembly and then describes the semantics of this assembly in LLVM IR, which may sound weird, but LLVM IR is also low level, so we use it as kind of as a verification IR. Then we use LLVM itself to optimize this IR. So we kind of rely on LLVM to not remove bugs from this lifted IR. Okay, it can introduce new bugs, that's fine, but hopefully it should not remove bugs. And then we take this input IR and the lifted IR, give to Alive2 and check whether it's a refinement or not. Okay, so that's roughly how it works. I'll give a quick example. So we start with some IR function. We compile into assembly. And then our tool takes this assembly, produces a much larger IR, right? Because now you have all these bit fiddling things. There's also a bunch of redundancy, and that's why now we use the optimizer to shrink this. And then we ask whether there is a refinement relation between these two programs. Okay, so focusing now on the lifter. So if you want to write this lifter by hand, it's a lot of work because current CPUs have like thousands of instructions. And so it's going to be a lot of work, and the probability that it's going to be wrong is like 100%. So, so we didn't really want to do it by hand. So, but fortunately, ARM has a machine-readable spec, so, which is quite complete. Okay, being quite complete is good, but is also a curse because it has a lot of detail that is not interesting to prove the correctness of a compiler backend. So we use partial evaluation to remove a lot of the detail that is not interesting. For example, we are validating code to be used in user mode. So all these checks whether the instruction is running in kernel mode or user mode or whatever, like we can optimize those out. To give an example, so here we have a specification in this ASL language. This is a vector instruction, so it has a loop over the elements of the vector. And we take these and we generate this compressed version of the specification. And then essentially when we see an assembly instruction, for example, when we see these adds like with vectors, essentially we have a sort of interpreter that goes over the spec and generates these IR. And note that we don't have any loops anymore, but we are actually generating IR, which does vector operations. Okay, so besides checking that it's generating the right assembly, it's also very important to generate that is ABI compliant. So ABI is that spec that allows you to link files that were compiled from different compilers and allows you to call a function and know what state is kept, what state may not be kept, right? And so bugs in this part of the code are really horrible because you may get one wrong bit somewhere and then you don't know where that wrong bit is coming from. So we also implemented checks to make sure that the ABI is being followed. And we found bugs in this part of the code of LLVM. And this verification is the style of rely guarantee, because when you call a function, you kind of rely on that function following the ABI, and then you need to ensure that the function you are verifying is also following the ABI. Okay, so now going a bit on the verification side. So we use Alive2, so we didn't have to re-implement all the verification algorithms from scratch. But there's a little catch, which is the IR that the lifter generates is valid, okay? It's perfectly valid, but is not a refinement from the original IR. And the reason is assembly has a different memory model than LLVM IR, and it's not possible to express this memory model in LLVM IR, or at least not in a reasonable way, okay? I'll just give one example. So if we have this function where we store to P if P and Q are equal, otherwise we store to Q, what LLVM generates is just a store to Q, right? Because when they are equal, it doesn't matter whether you store to P or Q. When they are different, you store to Q, okay? And LLVM is smart enough to generate that assembly. But if you lift that assembly naively to an IR store through Q, that's not equivalent to this problem, okay? And this is about pointer provenance, so I think that's a long story for some other day. But it's essentially we cannot naively do that lifting. So what we did, we implemented a flat memory model in Alive2, and we extended the refinement check to be able to do refinement between programs using different memory models. And also importantly is the optimizations, because SMT solvers are not magic boxes. If you throw random SMT, they don't work. So when we start working on these, nothing was verifying, of course. And then we implemented a couple of optimizations to make it work. Okay, so just to conclude, hopefully I've convinced you that compilers have bugs like any other tool, but compiler bugs are a bit more scary because they can introduce security vulnerabilities silently in your compiled programs. So we caught actually the same bug twice because the bug was fixed in LLVM and then someone reverted the fix. And so we got the same bug a few months later. And so I leave up to you whether that was an accident or not. And then translation validation is a practical approach to identifying bugs. So it works fairly well. So our tool, ARMTV, already found 45 bugs in the ARM64 backend, but also in the generic backend code. And so it just reuses existing verification framework, so we didn't have to implement all sorts of verification algorithms. And just to reiterate, checking ABI compliance is super important. There are a lot of bugs here, and they manifest in very weird ways. Okay, that's it. Thank you for listening.
Yeah, for questions, please.
Okay, nice talk. And I'm wondering if you can extract the backend specification from other architectures such as the x86 because they have table gen. Yes.
Let's see. Actually, we are working on a RISC-V implementation right now, but using LLVM table gen files is not sufficient because the semantics is not is not sufficient because they are don't care bits. There are all these other things that table gen does not, because table gen is a refinement from IR to assembly. It's not an equivalence, right?
Mm-hmm.
But what we want is the other way around, is a refinement from assembly back to IR, right? And so table gen, maybe you can have, can go a long way, but it's not sufficient.
Okay, so this work is mainly for ARM, right?
Yeah, if you can have complete spec, it's fine. Like if you have a partial spec, then there are no miracles.
Thanks.
Hi, thanks for a great talk. I have a rather practical question. So you said you assume that you don't remove any bugs in your translation. Does that actually happen? Like, do you have an intuition? I mean, if you do remove it, I assume you just miss the bug. But since you're not verifying it, but validating, it's okay. But do you have an intuition how often that actually happens?
So that thing, is LLVM, and this is where Alive can actually check whether that optimization is correct or not. So, I mean, we have already used Alive a lot in LLVM, so I think by now we have a good understanding where the bugs are. So I'm not too concerned, but it's a theoretical concern, but I think practically, I mean, if you really want, you can run Alive there as well. Right? But just maybe a fun story is, like some years ago, we were cross-checking Alive using Z3 and CVC4 at the time, and actually Z3 proved an optimization correct, and we only found by cross-checking with CVC4. And this was a one-character fix in Z3 that made, it was like some copy-paste error that made Alive prove an optimization correct. That was wrong. So things happen.
Okay, I get that. Thank you.
Let's thank Nuno.
Thank you.
And the next speaker is Mao Lin, and he is going to validate SMT rewriters.
Okay, thanks Stephen for the kind. My name is Mao Lin, a PhD candidate at Nanjing University, and I'm advised by Yibiao and Yuming. It's an honor to speak at OOPSLA and to share our recent research. The title of my talk is Validating SMT Rewriters via Rewrite Space Exploration supported by generative equality saturation. Okay, before diving into our work, let's start with some background. Okay, our work focuses on SMT solvers, the tools that are designed to solve logical constraints. And here is they take formulas written in the SMT lib language as input. And here is a very simple example. Here we declare a variable x of type integer, and we add a constraint x greater than 0. And finally, we ask the solver to check satisfiability, and the solver responds satisfiable for this case. And if needed, it can give a concrete solution like x equals 1. And over the past decade, SMT solvers have become very, very powerful. They now support a wide range of applications like program analysis and formal verification. And in fact, the previous presenters' great works are also made use of SMT solvers for verification, and showing just how broadly these solvers are applied today. And their impact is so large that the 2015 SM Programming Languages Software Award went to Z3, one of the most widely used SMT solvers in the community. And in industry, SMT solvers are also everywhere. For example, Amazon calls SMT solvers 1 billion of times every day to help ensure the security of their system. And it clearly shows the solver reliability and quality are essential. So many research have contributed excellent works on SMT solver testing, but one part is often overlooked. That is the rewriter. And the rewriter isn't just important for SMT solvers. You will also find rewriters in other major software systems like GCC and LLVM, where they play a very important rules in program optimization. Yeah. So what exactly is a rewriter? The rewriter is the engine that simplifies formulas. It applies a lot of rewrite rules to transform formulas step by step into forms that are easier for solvers' core engine to handle. Yeah. Developers of SPLASH'25 have even said improving the rewriter is as important as improving the solver's core decision procedure. And if the rewriter is buggy, the impact can be very, very serious. And here shows an example. This formula on the left looks very simple, right? Yeah. But surprisingly, these three reports are unknown for it, meaning it cannot decide whether the formula is satisfiable or not. And after a closer look, we found the root cause, a missing rewrite rule. Yeah, in fact, if we replace A inside an empty string with another empty string, the result is still an empty string. So the formula can be rewritten into the simpler form on the right, which the solver can easily solve. And this shows the missing rewrite can cause completeness issue in solvers. And to further investigate the importance of the rewriter, we conduct an empirical study. We examined more than 8,000 pull requests from the SPLASH'25 project over the past 10 years. Surprisingly, about 14% of the pull requests were related to rewriters. And if we check their priority levels, around 18% of the rewrite-related pull requests were marked major or normal by developers. This aligns with the developers' views that enhancing the rewriter is very important. But despite its importance, testing the rewriter is difficult. Two main challenges stand out. First, how do we make sure our test inputs really trigger rewriting? You know, without broad coverage, some rewrite rules might never be exercised, so leaving hidden bugs undiscovered. Second, even if we trigger rewriting, how do we check correctness of the solver's output? To tackle these challenges, we propose a two-phase method. Phase one, mimetic mutation. In this phase, we mutate the seed formula to match the left-hand side of rewrite rules so that more rewrite can be triggered in next step. And phase two, deductive rewriting. Here we will use equality saturation to explore the rewrite space and generating many formulas that are semantically equivalent. Together, these two phases make it possible to thoroughly test the rewriters. And our method should rely on a set of high-quality rewrite rules. So, where do these rules come from? In our work, we use two main sources. First is the existing rules implemented in SPLASH'25, collected by peer study. And second, synthesized rules generated by Ruler, which is rules that infers new rules from existing ones. The second source is particularly interesting because these rules may reveal new rewriting opportunities that solver developers may not have implemented yet. However, rules synthesized by Ruler may not be always correct under SMT semantics. So we design an automated validation process. So for each rule, we construct a corresponding formula to check whether the rule ever produces a contradiction. We then cross-validate them with multiple solvers. For example, for the rule, first rule, 0 plus t equals t, we can check if there exists an t such that 0 plus t is not equal to t. If all solvers return unsatisfiable, the rule is valid. And now, let's take a closer look at phase 1, mimetic mutation. We start with a seed formula, and from it, we randomly select a subformula and modify it so that it matches the left-hand side of a rewrite rule. In this example, on the left is the original seed formula. And we mutate one subformula such as R, and the result is the formula on the right. At this stage, we don't guarantee semantic equivalence. We just increase the chance of triggering rewriting. Yeah. Phase 2 is deductive rewriting. Here we leverage a technique called equality saturation. We build an equality graph, also known as E-graph. And each dashed box here in the E-graph is an equivalence class, containing nodes that represent semantically equivalent formulas. Initially, each class may have only one node, as shown in the figure. And we then repeatedly apply rewrite rules. As we do this, the E-graph keeps growing, discovering more and more equivalent versions of the seed formula. And in fact, the E-graph shown on the left hasn't reached saturation yet. Saturation happens when no rules can further change the E-graph. At that point, we have explored the full rewrite space given our rule set. And once the E-graph is built, we can extract many equivalent formulas. And because these formulas are guaranteed to be semantically equivalent, we expect the solver to give consistent answers for them. And if a solver's output differs, we flag it as a potential bug. Besides, two more design details may be also worth mentioning here. First, equality saturation engines are typically designed for optimizations. That means they typically simplify formulas, not make them more complex. But in the context of testing, we also need rules like rewriting 0 to x times 0, which will introduce new variable. So we modify the equality saturation engine to support this kind of rewrite. And second, we design a sampling strategy for extracting formulas from the E-graph. We give high priority to variants that are structurally different from the original one. This may allow us to trigger more rewrites and improve our ability to find bugs. And if you are interested with these technical details, please check our paper for more information. And finally, we implemented our approach as a practical testing tool called Arrays. We evaluated it on two state-of-the-art SM solvers, Z3 and CVC5, using the seed formula from the SMT-lib official benchmarks. And here's the result. Our tool found 27 unique issues, and 22 were confirmed by developers, and more than half have already been fixed by developers. These issues covered correctness, crashes, completeness, and performance. By checking developers' fixes, we confirmed that most of the issues were indeed rewrite-related. And this showed our method effectively targets the rewriter. We also ran an ablation study to evaluate the contribution of each component in our tool in terms of triggering rewrites. We built three variants here, one with only phase 1, one with only phase 2, and one with only the rules generated by ruler. In all cases, effectiveness dropped significantly compared to the full method. This confirms that all components are necessary for our approach. And finally, let me show a very simple case discovered by our tool. Here, this will return the unknown for the formula on the left, but the formula is always true. It indeed checks whether the empty string is lexicographically less than or equal to another string. So the formula could be rewritten to the simpler formula on the right. And we report this issue, and these 3 developers accepted our suggestion to add a new rewrite rule for it. And this shows our tool not only find bugs, but also directly help developers improve their system. And that's all. Thanks for your listening.
Do we have a very quick question?
Hi, thanks for the talk. When you use equality saturation, do you test multiple rules at one time or just one?
Multiple times. Yeah.
Multiple.
Yeah.
So if you find a fault, how do you know which rule is faulty?
Actually, we have designed a very simple debugging process. Also utilize equality saturation, and we, considering the time limitation, I don't introduce our approach here. If you're interested, you can check our paper.
Yes. Okay. Thank you.
Thank you for your question.
All right. Thank you very much. That closes this session. Just right next door is now the award session. So if you want to know who the distinguished papers are, please head over to the right.